Welcome in another problem solving session of TIFR. The problem that we have in front of us is a very neat problem. So it can be solved in many different ways, but the procedure that we are going to follow is through the dominated convergence theorem. So let us first see what dominated convergence theorem is, and then I will try to point out where we are actually using it. Dominated convergence theorem is something that is very essential in these type of problems if you encounter in future. Okay, so it kind of relates to the in limit with the integration. The commutativity of the limit and integration are, uh, I mean, understood by dominant convergence theorem to some extent. So in this problem, before going, so let us first see what dominated convergence theorem is. Dominated convergence theorem. So it's in short, it's also known as the DCT. So to understand the dominant convergence theorem in its full glory, you need to understand uh, measure theory to some certain extent. But uh, I will try to keep it restricted to the portion up until which we undergraduates study. So I will write down the full general statement, and then I will show you that for which type of functions specifically this can be also used. So the general statement is, let Fn be a sequence of complex valued measurable function that converges pointwise to F. So that means there is a pointwise convergence that Fn maps to F and is dominated by an integrable function g such that mod of Fn of x is less than or equals to gx. Okay, so that is why it's called as dominating. So the sequence of functions values are being dominated by this function g. So if this happens, then f is integrable and the limit commutes. So that's the interesting part, that limit n tends to infinity. So let's say over some s fn. So this becomes limit n tends to infinity fn over the region s. So which is nothing but s over f. So as you can see that the dominant convergence theorem uses two tricks. That is, the first requirement is has to be a pointwise convergent. There has to be a pointwise convergence, and there has to be a domination by an integrable function. So now measurable functions in undergraduate level are the main two sections are continuous functions and integrable functions. So both these type of functions are always measurable functions. So this is the general dominated convergence theorem, but we can actually use it in the undergraduate level for continuous and integrable functions. So now let's see what the problem is, how the problem is been presented to us. So we need to understand what is the limit of this. N tends to infinity, n square 0 to 1, 1 by 1 plus x square whole to the power n dx. So this is something that we want to understand. So now the fact is that, see, if I can somehow show that the integral can be computed using the dominated convergence theorem, then I can directly apply my limit. That's the idea, because as you can see that limit n tends to infinity is on the outside. So now what most of us always try to do here is to use the in hospitals formula in this type of scenarios. So what happens is that the numerator and the denominator, they are both going to infinity, but you have to do a lot of El Hospital's procedures to, take yourselves towards what you want as an answer. Okay, but here, see, I will just break it into two simple things. Let's take into root over n 0 to 1, 1 by 1 plus x square whole to the power n. So now this part is a pretty famous integral. So if you are very familiar with the gamma function, using the dominated convergence theorem, we will use the gamma function to prove that this part is always root over pi by 2 when n tends to infinity. So since this part will always tend to infinity, combined they will tend to infinity. So that's the gist of the problem that we have here. Okay. So how will I actually show that the square portion is root pi by 2? So let's now dig a little deeper. So let's take as I n to be this root over n 0 to 1, 1 by 1 plus x square whole to the power n. So now take this. So take x square equals to p by n and just substitute it. So if you substitute it, then what happens? You have 2x dx equals to 1 by n dt, and then x becomes root over of p by n, basically 2 root over of p by root over of n. This is 1 by n dt. So, dx. So then dx becomes half root, sorry, half 1 by root nt dt. So this is what you have. Okay. So now if you just replace it over here, everything, so you will get something like this. This is half 0 to n 1 by root t into 1 plus p by n whole to the power. Now as you can see that this part now is more familiar to us, the inner side of the integral, because as you can see 1 plus p by n whole to the power n, n tends to infinity is goes to e to the power t, this part, right? So now what I need, so here what I need to use to kind of position myself in order to use dominant convergence theorem, I need this g. I need an integral in g which actually dominates my in, correct? That is how we will use the dominated convergence theorem. So how will I construct this? So this now becomes half 0 to 1, 1 by root over t 1 plus t by n whole to the power n plus half 1 to n 1 by root t 1 plus t by n whole to the power n. So now see, the way I have actually positioned myself in these two integral, this is strictly less than half 0 to 1 by root t plus half 1 to n by root t into 1 plus t. Reason is, here the limit is from 1 to n. That is why this element is bigger than this always. And since it's in the denominator, if I just replace it, then I will have and greater than equals to sign. So now this function is integrable. So you can actually integrate it. I mean, it's quite clear that this function is integrable. So this entirely becomes my g. So now this is my g, which is an integrable function. So this is my g. Okay, so now this becomes my integrable function. Hence, my in is dominated by this g, which is integrable. Now, the only thing is to understand is that where does the sequence converges pointwise, right? That's the first thing that we have to check. So, if you take 1 by root t, 1 plus t by n whole to the power n, limit n tends to infinity, where will it converge? It will converge to 1 by root t e to the power t. So, now we have that all the DCT criterions are satisfied. Hence, what do you have? Hence, the integration, it is integrable and the limit can go inside. And the limit can go inside. So the moment the limit goes inside, what happens? You have this. 1 by root t e to the power t 0 to infinity. This precisely becomes your in limit n tends to infinity. So what is this? This is the half. So now 0 to infinity e to the power minus half e to the power minus t. This is gamma of half. So the moment I have gamma of half, then this integration becomes my root pi by 2. So from the moment we started with limit n tends to infinity, here this thing shoots to infinity, but since this part becomes bounded, I mean, since it's integrable as it tends to infinity, it is always bounded. So the only unbounded part takes the entire integral to the infinity. That's the point. So this part is integrable. It has it has a bounded answer. It's an answer that is not infinity. Hence, the integral is bounded. So the only unbounded portion here takes it to the infinity. Hence, here the answer to this question will be tending to plus. Okay, so that's it for today. Thank you for joining us. We will meet next time with another problem from TIFR.